Okay, before I start, I want to thank Sprout Social for hosting the event and all of our sponsors and the board of Chippy, and of course all of you for being here. I'm really excited to give this talk. This is an area of life that I'm very passionate about, but also it has an intersection for me with two of my great loves, music and sound and Python. So I hope that some of that passion rubs off on you and you're interested in exploring this stuff. And after the talk, of course, I'm going to be available for any chatting and questions you have. Of course, I'll take questions after, too. So briefly about me before I start. The composer Harry Parch once said, I'm a musician who's been seduced into carpentry because he was, he built all of his own original instruments because the things that he wanted to do with music weren't available with the typical instruments around him. I'm a musician that's been seduced into coding. So my master's degree is in piano performance, classical piano. So for me, the fundamental, the thing that really gets me in life is music of all sorts, especially classical music. But I also love electronics and all geeky things, and I love electronic music and so forth. I went to Northwestern, got my degree in piano performance from Northwestern, my master's degree. Before that, SUNY Purchase. Anyone here from New York that knows the SUNY school system? There we go. Good, thank you. That one person. Right now, I'm on assignment through Tech Systems at Bank of America, doing financial calculations in Python and so forth for remote risk. Before that, I was working for a little company called National Education Servicing, student loan servicing company, who sadly went out of business in June. So I hopped on to my next gig. Anyway, let's talk about why we're here. Does anyone know what DSP means?
Digital signal processing.
Good, thank you. So basically, Python has a nice library that this guy, Olivier Bélanger from Montreal, if you know anything about the scene in Montreal, there's a heavy electronic music scene up there. And Olivier is part of that scene, and he's a Python guy. And this is basically a C-level library. I won't, pull any punches in saying, raw Python probably couldn't handle some of the stuff that, as much as I love Python, the real advantage of using Python for this kind of work is as it shines as a glue language, as we all know. Heavy lifting is done by Python, and the grace is done, heavy lifting done by C, and the grace is done by Python, is the way I like to look at it. So, digital signal processing, DSP. Some basics, and I'm sorry if some of you already know this, some of you may not, so we're going to go, not at a snail's pace, I'll kind of go through the basics first, just so we're all on the same page, okay? So forgive me if you already know some of this. The use of digital computation to perform a wide variety of signal processing operations. Signals are a sequence of numbers, and they're in the computer and obviously in the memory, and they represent various domains, such as time, space, frequency, okay? Typical uses, audio and speech processing, which is what I want to talk about. You also have scientific uses, lots of things like, I want to measure, atmospheric disturbance and figure out something about the signal, and maybe there's something that's telling me that there's a UFO in the clouds or something, I don't know. So I write at the end, blah, 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 blah. I don't want to go on and on, but you can see some of the many things. This is all stolen from Wikipedia, that definition, I'm very sorry. So, giving you the context for which PyO comes onto the scene. Some of you may know some of these packages. FOSS, of course, represents free open source software. So I encourage all of you to explore this. There's some amazing packages for music and sound work as well as general DSP. Csound and CMix, et cetera, are from what's called the Music 5 heritage. There's a guy named Max Matthews from Bell Labs way back in the 50s that started coding all this stuff. He's the godfather of all this. You have Super Collider, which is a well-known package. more geared towards real-time work. You have Chuck from people at Princeton. There's a guy named Miller Puckett who worked over in IRCAM in France. Does any of you know, have you ever heard of IRCAM? Have you? Okay. It's a famous electronic music lab that was led by Pierre Boulez, who was a famous, he recently died, but he was a famous conductor, composer, et cetera, and kind of an avant-gardist in classical music as well as in electronic music. Miller Puckett comes from that IRCAM scene, and he wrote a free version of Max MSP. It's called it PD. There's also a commercial version, as you see down there. And then there are various libraries. This is by no means a complete list, but it just kind of gives you the context of what PIO is and where it's coming onto the scene. Probably many of you have heard of Reactor, Native Instruments synthesizer suite, and then there's also Kaima by Korg. I just mentioned it because those are heavyweight names. So just a basic idea of what DSP is all about and what it does. If you have, let's say my microphone is taking my speech and I want to put some reverb on it, okay? You can have a reverb plug-in or what have you, a process in your DSP software that would actually read my input and put it through what's called an analog to digital converter. This is where the magic happens on your laptop. And the DAC is the digital analog converter. Every computer has a DAC, the exit point of which is your headphone port. And of course, that is an analog signal. So you're taking things from the analog domain, putting them to the digital domain, possibly processing them, putting them back out. However, this is not the complete picture. Not everything has an analog in, right? We'll create a signal just purely here. We don't care about input. We want to just take a square wave or a sawtooth wave and start making music with it. So in which case, that would just be starting in that middle block. Pretty basic. Okay, just basic review. All sounds are pressure waves. Does anyone know what kind of wave this is, the shape of it? Sine wave, right? And just to review, in case you're rusty, one of the basic aspects of, let's just take sine waves as an example. Frequency and wavelength are inverse proportion to each other. So the shorter the wavelength, the higher the frequency, vice versa. Amplitude is loudness. That's dictated by the height of the wave in the kind of metaphorical y-axis. So when you hear a louder sound, you visualize that wave as being taller. Okay? That example in the corner is an example of a periodic waveform that might be produced by a clarinet. Okay? And then finally, one more educational slide. A sample is a fundamental unit of DSP. It's basically like Ginsu knife chopping the wave and creating a stored value. Okay, so here's your continuous signal. You have what's known as a sampling rate. Okay, so like your CD, when you listen to a CD, if you listen to CDs anymore, apparently LPs are coming back. But anyway, if you listen to CD or a raw wave file, you're going to have something that's like this in your memory. Your continuous waveform is going to be sliced and diced, and the resolution by which you play it back, it has to do with the sampling rate. And like it says here, typical CD quality audio uses 44-100. That's a typical sampling rate. I won't go too deep into this, but the reason we choose 44-100, does anyone know? Yes? That's correct. There's a thing called the Nyquist frequency, which I didn't put down here. We want to represent the highest frequency, but we want to double it so that we actually get a sense that the most basic wave that we can have in 44-100 is a 20,000 hertz signal for the human hearing, right? So like typical human hearing range is up to 20,000 hertz. So if we want to represent a wave like that, we need to double the rate so that we actually at least get two samples, maybe the top and the bottom of it. So storage-wise, when you have 44,100 samples at 2 bytes, let's say it's 2 bytes of resolution and 2 channels of stereo and 60 seconds of that, that means a minute of uncompressed audio is 10.58 megabytes. Of course, we compress a lot of audio and all that stuff, but that's beyond the scope of this conversation. Who knows what that is? Yes, those things are super cool. This is basically an old-fashioned Moog type. This is the early days of synthesizer look. Now people, because things are retro and cool, these things are like very expensive gear now. They're analog. They typically don't have any memory, so if you make a patch, you have to write it down and so forth. There's ways around that, but you basically have a bunch of oscillators and filters and all that stuff, but and patch cords to route them. And they're super cool, and a lot of the music you love uses something like this. If not that architecture, it's like sort of hardwired, like any hardware synth that you buy kind of follows this paradigm. So the semi-punchline, basically Pio or any other DSP library that does synthesis allows something like this to look like this. And I'll just walk you through some of the basic ideas. This is by no means as complex and as cool as the thing you just saw, but in Pio, you just import the namespace of Pio, the whole thing, because you want all the functions, all the objects. So forgive the fact that it's not server. I know that's not Pythonic. Just doing the S, very simple. So you set a server up, and in this case, the audio is routed to a library called port audio. Duplex equals 0 simply means we don't care about input, we're just going to do output. You set the MIDI input device. I didn't bring my keyboard, but that might be like, hey, if you do a scan on your computer, this little input keyboard lives at this port, so that's what the 2 is. I boot the thing. This is a listener. It's listening for MIDI note events. So if I hit something on the keyboard, it's in a listening mode, and it responds, and it has a callback to something else. This is an ADSR, which means attack, decay, sustain, release. In synthesizers, you can have an instrumental sound that's like, bing, right? That has a fast attack. It's barely, it's almost instantaneous. It's like hitting a chime. Or you can have like the bow of a string, wah, right? So that's a slow attack. So those different things are parameters here. There's attack, decay, sustain, release. We didn't do attack. I guess there's a default in there that's like 2 milliseconds attack. Here's an ADSR for the filter. So if you listen to techno music or whatever, the effect of the filter is like, how we hear like things that get dark and bright. That's what the filter is doing. It's opening and closing the spectrum. This is an oscillator. That's a filter. I'm panning it left and right. I have a reverb. Then I open the GUI, and I can control it. So it's kind of cool. You're going to get to see some of this in action. Let's do a fun, basic example. An overtone series viewed with an oscilloscope. What does that mean? Does anyone know what the overtone series is? Anyone? Wow, okay. The harmonic series, any periodic waveform has basically an arithmetic series to it. So if I actually sing a pitch of like 200 hertz, let's say 100 hertz because it's easy to do the math. Since the human voice has a periodic waveform, it has what are called overtones or partials in it. So besides the 100 hertz main sine wave, there's a 200 hertz, a 300 hertz, a 400 hertz, a 500 hertz, a 600 hertz, 700, right? All whole number multiples, roughly. And those have different strengths, and they add to the signal and create a certain spectrum. So let me bring up Pio and show you what this all means. So one of the things we'll be doing is we'll build a sawtooth and a square wave. We'll show you how sine waves are the basic component of all sound. And you'll see how beautiful and hypnotic waves going in and out of phase look. And you'll see it on the oscilloscope because it's cool. Oscilloscopes are cool. Can you all hear that? All right. Not very interesting so far, but just you wait. Okay. Okay, so this is sort of like a sawtooth wave. It looks like a sawtooth, right? And every sawtooth wave has, if you look at the shape of this, the first harmonic is 1 over 1, the second harmonic is 1 over 2, this is 1 over 3, this is 1 over 4. So it has this kind of like 1 over x shape, right? If I take out the odd harmonics, I get a kind of reedy clarinet-like sound. It looks like a square wave. Can you all see that? Yeah. Okay. And then, where are you? Okay, here we go. This is, I'm going to detune this. This is fun. Pretty, right? So what happens is the phase, I have another wave interfering with it, so you can see the wave cancellations, right? The whole wave is, you know, if I set this to 0, it's in a kind of a steady state. But when I do that and detune it, you can see how they move in and out of phase with each other, okay? Will this be the best Chippy meeting ever? Yeah. I've got a little fun thing here. Let's see. Okay. Yes, that has the Chippy meeting. Okay, so who doesn't love a robot voice? We all love it. It's a cheap thrill. So there's not a lot of real estate on the screen here. I'm sorry, I'm going to pull this down. So this is what's called a vocoder. Can I get rid of this? I can, yeah. And so I have a file here that I recorded with my voice just saying that. I'm not saying it over and over. I'm not that bored or weird. It's actually looping. That's why it says loop is true. And finally, there's some exciters, a noise and a sine loop. We've got some modulation waves happening here, which is why the sound is changing over time. I feed it into a vocoder object, and it gives you that kind of wonderful robot sound. Okay? And I know I only have a couple minutes left, so I want to show you some cool other little things. Algorithmic. So here's a drum machine thing. So these arrays of ones and zeros are hit, don't hit. And you got some algorithmic stuff happening that, you know, every once in a while mixes it up and changes. That's what this callback change is doing. So that's in the examples here. If you download Pio, all this stuff is here. Obviously not the best Chippy meeting ever. I kind of altered that file. So yeah, in the remaining couple minutes, I'm going to stop this. In the remaining couple minutes, I wanted to show you, I want to skip ahead. Obviously, I won't get to talk about microcsound. I didn't realize the time. Maybe I can come back and do that at some other point. Let's see. Here we are. Okay, you know who this guy is? Yeah, Brian Eno. He does ambient music. So I've written a couple of ambient pieces, and I'll just give you a taste of them. They were done with Pio. Pio is really wonderful for this kind of thing because you can kind of set things up and tweak them and go and listen to the soundscape evolve. So let me show you one. Chippy. Okay. Yeah, I call it Cloud Zone Alpha Prime. It might be instructive, I'm sorry to talk over it, but it might be instructive for you to see what's happening in the code here. So I can bring that up. I set up some lists, and the main driver of this texture is this object called cloud. Has a density parameter which tells you how many events per second it's going to do, has a polyphony parameter, how many layers are actually possible total. And there's some triggers that happen. A lot of thought goes into this. It's not like you can just say, oh, I'm going to take this and go, you know. You tweak it over time, but basically the whole idea is that you play with chance procedures in a way that as long as you set things up in a nice way, you get something that's really pleasing to listen to and or interesting, and the trick is to set it up so that it is interesting and listenable and you don't get really annoyed at. So, and that's that.